Welcome to our discussion for fluids in motion. Today we shall look at fluids in motion, different from what we have been discussing, static conditions. Now, when we are talking about fluids in motion, we are looking at displacement, how a fluid is moving from one point to another. Now, when a fluid is moving from one point to another, there are things that should be put into consideration. That the viscosity will play a part on its behavior, the shear forces that were the shear forces as a result of fluid movement between the particles will actually also cause what we're calling friction. Now we have fluids can be categorized into two forms. We can say our fluids are either in ideal situation, and this is when we don't look at viscosity as a component that is playing a part in fluid flow, or they can be real where everything is actually considered, including shear stress, friction, and other components. Now, when we're discussing fluids, usually there are key things that we should be looked out for. And these key things are usually definitions. It is important for us to note that we need to know what a path line is. And we're saying that a path line is a trace. It's a trace showing, we are looking at positions of particles along a flow line. So those positions at successive intervals of time of a particle, we are calling them path lines or a path line. And also we have what we call a streamline. And usually a streamline is if the path is a particular point, then it means in a streamline at that particular point which separating streamline, there is no flow. So we're saying it's an imaginary curve in the fluid across which at a given instant there is no flow. So that one there we are calling it a streamline. And this is a stream tube. We're trying to show that in between these one there will be particles moving, which is a path line, and therefore these lines drawn actually depicting what we are calling a streamline. Now, flow, when we're talking about flow, it will occur in different ways. A flow can either be uniform flow or it can be steady flow. Now, we could grasp these components from two perspectives. Is that if we describe flow as uniform, then it means we are going to look at it from a perspective of properties of flow that are changing from one point to another. So if the properties of flow, that is the velocity, the cross-sectional area, if those components are remaining closer from one point to another, we're saying then we have uniform flow. If they begin to change from one point to another, if the velocity, cross-section area, is changing from one point to another, then we're saying that is non-uniform. When we come to steady steady flow, we're saying that these flow parameters, velocity, pressure, cross-section area, will not vary with the time in this case. So the time component is not the properties are not changing with time. So it means that if the two things occur, then we can have either uniform or non-uniform. But remember, in flow, it is the two things are occurring together. The point, from one point to another, it's occurring at the same time. Also, the time surpasses. Now, it gives us the practice of classifying our flow in form of steady uniform flow, steady non-uniform flow, unsteady uniform flow, and steady non-uniform flow. Now, this kind of thing here means that for steady uniform flow, it means all the properties or the parameters that determine flow are remaining the same from one point to another and also with time. And we're saying that this kind of thing, it takes place when the pipe is of a uniform bore and water is running at constant velocity throughout the pipe. So assuming the pipe is all rectangular, sorry, is all circular, and the velocity in the pipe is the same, then we shall have steady uniform. Now, steady non-uniform is that the conditions change from point to point but do not change with the time. So we're saying that the velocity, cross-section area, and everything are changing from point to point but not with the time. And we're saying that this can be seen from a perspective of a tapered pipe. So if you pump water through a tapered pipe running completely full, then we are saying that we have steady and uniform. And we're saying that unsteady uniform flow is if you run a pump. When the pump is starting, usually the velocity is increasing until it reaches a point where it is stable. So before you attain the steady uniform, then you come from the unsteady uniform flow, which we are saying that at this particular point, the parameters of flow are remaining constant with time, but sorry, are changing with time, but remaining constant from one point to another. And also when we look at unsteady non-uniform flow, this can be captured from the perspective of a wave. A wave is unsteady non-uniform flow, or if you look at the flow of water or storm water in a in a channel. Usually this is what will happen. Now we say that fluids can be either real or ideal. So we're saying that if the fluids are real or ideal, there are things that are important for us to know. That when a fluid is flowing, it's going to experience friction on the walls of the pipe. So if it's going to experience friction on the walls of the pipe, then we are saying that there is going to be a thickness that is going to experience friction. And we're saying that that thickness that is going to experience friction, we're calling it a boundary layer. But that boundary layer has a particular thickness. And we're saying that that thickness will be equivalent to 99% of the stream velocity. So by the time where the water reaches 99% of the flow in the center, because the friction is going to begin reducing inwards until the velocity is 99%. So anything below 99%, the maximum velocity, we are saying that that is going to be called the boundary thickness. So that that thickness of the boundary layer is important when we're dealing with flow. But under ideal conditions, the thickness of the boundary layer does not matter. Now, when we're discussing flow, we are looking at we are looking at incompressible fluids are not compressible. Now, fluid flow can be categorized in 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 different forms. That we can experience flow in a one-dimensional scenario, or a two-dimension, or even a three-dimension. So if we look at a Cartesian equation of x, y, z, is that flow can be only recognized in the direction of flow, which is x. But also you could look at flow from the perspective of x and y. Flow on the surface, moving horizontal in the y direction, and also moving in the flow direction. But it could also be in a scenario where it moves downwards, like a waterfall. In that case, you'll be looking at the velocity and also the fall. So usually, under normal circumstances, ideal situation, we assume that the velocity is the same from a wall to wall, but in a real, it may necessarily look like this. Now, also, it is important for us to look at flow from a perspective of laminar and turbulent flow. Usually, laminar can be looked at as a streamline or viscous. So when we are discussing this kind of flow, we are saying that we are describing flow from perspective of streamlines. We're saying that if streamlines are parallel to each other when water is flowing, then it means we're experiencing laminar flow. But if they are not parallel, then the reverse is true. Then we are experiencing turbulent flow. Now, this turbulent flow it can be a relationship that is derived. That we're saying that the description of categorizing flow as either laminar or turbulent was proved by a gentleman called Reynolds, and he called it Reynolds number. So the Reynolds number is looking at the density, is looking at the velocity, is looking at the characteristic length, how long your where your water is passing, that characteristic of your conduit, and also what we are calling the coefficient of dynamic viscosity. This one we described it, we defined it earlier. Now this value here is that if this formula here gives you a value that is less than 2000, we're saying it is a laminar flow. If it gives you a value that is greater than 4000, we are calling it turbulent. And the intermediate, we are calling it transition flow. So that kind of thing is important for us when we are describing flow properties, or how the behavior of a fluid should flow. Then also we have what we call discharge and mean velocity. Now discharge is usually the volume per unit time, or mass flow rate, or how much volume of water is passing a particular point per unit time. And we say that the mean velocity is that, and the description of this kind of thing is that under real fluids it would behave like this, but because of ideal situation this is very hard to determine, so we usually use mean velocity. And that mean velocity is what we're trying to describe here, is that if we had a pipe and we assume that there is a small strip which we're calling dr, and it is it is at a radius of r from the center, and then the maximum radius of the pipe is r, and we do a differentiation by saying that the discharge is given by what we are saying is given by area times velocity, or cross-sectional area times velocity. So the area of the element times velocity. So we know that the velocity would be u, but the cross-section area would be equal to the circumference of this element, which is 2 pi, r, and then times the thickness dr. If you get this strip and then split it, the thickness will be dr, and then the length will be 2 pi r. So we're saying that that if you integrate it, then you will get this kind of equation. And we're saying that the velocity we're using there would be the mean velocity. So we're saying that mean velocity is given by q over cross-sectional area. Then also we have what we're calling continuity, that assuming this was our control volume or our body, maybe a reservoir, and then assume that water comes in and water gets out. If water comes in and you're assuming that by the time you are putting in water, the tank is full to capacity, and then if you pump in water and it exits, the time when inflow and outflow are the same, we are calling it continuity. So we are saying that the mass of fluid entering per unit time is equal to the mass of fluid leaving plus an increase. If this increase is zero, then we say it is continuity. If it is not zero, then it means there is a volume or increase in volume in a system. And this is what is going to happen, is that all the time we shall look at our system as from a perspective of two things. That if this was a pipe and we have continuity, and assume the pipe was the same cross-section area, and the fluid is the same, it means the velocity here and here would be the same, cross-section area would be the same, density would be the same. But assuming the pipe is tapered in this kind of form, is that we shall say that the mass of a fluid entering per unit time at section 1 is equal to what is leaving. So we are saying that if the density is the same, then rho 1 and rho 2 are the same. Therefore, they will cancel. But if they are different, then it means the equation will hold. So we are saying that at that particular point, we are saying that volume entering is equal to volume getting out. And it's the same thing, that whatever is entering here is equal to what is coming out from here and here. So A1 U1 is equal to A2 U2 plus A3 U2. So this is the equation of continuity. So we also have what we are calling momentum. Now this momentum is basically from the Newton's third law of motion. When we're discussing about Newton's third law of motion, and the second law of motion, we talk about action and reaction being equal. But when we're discussing about the second law of motion, we talk about a force. We talk about the rate of change of momentum is directly proportional to the force applied. Now, this is what is happening, that when a fluid is flowing, it has a pressure. When it has a pressure, it means it has a particular force. And the fact that the fluid has its own weight, then it means there's going to be mass conservation. And if there is mass conservation, then it means the effect of momentum must be reflected. And this is what is happening. Is that in this case, we talk about momentum as the rate of change of momentum, implying that it is momentum against time. And we're saying that is directly proportional to the, we say the rate of change of momentum is directly proportional to force applied. So it means if directly proportional to the force applied, then that means that our momentum can be, if it is per unit rate, if it is, sorry, it is per unit time, or is being reflected from a perspective of change in time, then it means the momentum is given by mass times velocity. But mass times velocity is momentum. But now, if we divide it by time, then what happens is that certain things will have to change. Now, it means in this equation here, we're saying that the rate at which momentum enters the control volume across AB is given by rho A1, U1, U2. So we're saying that if there is a rate of change of momentum, it means that the mass rate here, which we are calling m over time. So we are saying that mass times velocity is equal to momentum. But if we say mass divided by time, becomes the mass rate, which we are representing by m dot. So mass, which is mean m dot, which is going to be equal to rho A U, the same units, density is kilograms per meter square, per meter cubed, sorry. Area is meters squared, and velocity is meters per second. So we shall have a mass over time. So it means the change of rate of momentum, if it is from one system to another, from here to here, then it means it's going to be given by this. So when you summarize this, since the density is the same, you find that the cross-section area is the same if you add the continuity, and you find that the U is the same. So it means at this point that the mass here is going to be equal to m mass rate times the change in velocity. So we're saying that it means this formula here suits second law of motion by saying that the rate of change of momentum is directly proportional to the force applied, implying that the force is equal to the rate of change of momentum. So this is what we are basically having. Now we're saying that under normal circumstances, if it is a 3-dimension, then or a 2-dimension, then it is important for us to have a resultant force taking place. Now, in terms of flow, there are 3 things to follow. Is that when a fluid is flowing in a pipe, 3 forces will act on it. There will be an external force. There will be a force as a result of the weight of the fluid, which is a gravitational force. And also there will be force as a result of flow within the pipe. So the pressure will create a force, the fluid has its own weight, and also there's external force. So I'm saying that the rate of change of momentum is a combination of 3 forces. Force as a result of pumping or pressure, force as a result of weight or gravity, force as a result of external force, and we're saying that all the total should be equal to the rate of change of momentum. Now, assuming you have a fluid and is acting in 3 ways, is that there is a stationary bar, and then the fluid comes with a velocity v and hits a stationary system and remains there. And we have another one where it hits a bar which is already moving at a velocity u, and then there is another one where it hits a bar which is stationary and then moves with it. Now these are two things. These are three things. So it means if you hit this bar, the jet of water, if it has the initial velocity of v, the final velocity will be b. So it means now the mass rate, the force will be equal to the mass rate times the change in velocity, which is final v minus, sorry, initial v minus the final velocity, whereby our velocity becomes v squared. Now, if it is a system where this was already moving with velocity u, now if it was moving with velocity u, then it means that the mass of the fluid striking the fluid, the plate will already be reduced because already the plate is in motion. It is not a constant. So it means it's going to be equal to the mass, so it's going to be equal to rho a, but the mass rate is going to be equal to rho a v minus u because the body is already moving. But if it was initially the way it was, this u, the way the body was stationary, it would be 0. So it would be rho a v. But because the body is already moving, which you're going to hit, is that it is already reduced to v minus d. So the mass rate is going to be equal to rho a v minus u, again times the change in velocity, which is v minus u, because when it hits it, then it continues to go at the same velocity. But again, look, if it was a system whereby the body comes and hits a body, which is stationary, and then later it moves with the velocity u. So it will come and hit with rho av, and then it will move with a change in velocity. So we have these three components. So we have a body that is stationary, is hit by a jet, a body that is moving at a velocity v and is hit by a jet, and then we have a body that was not moving, and then when it is hit by a jet, and then it is constant, sorry, it keeps moving with velocity u. Now this, for people who watch football, is the same principle they use to stop the ball. Now you can imagine that this will give the smallest force, this will give a slightly higher force, and then this will give the highest. Now if you're stepping the ball and then your ball hits a stationary leg, it will bounce back. If you use this whereby your leg is moving backwards and then the ball hits, it will stop there. If you do this and first wait for it to bang and then move forward, it will move a shorter distance. So this is basically impact. The same thing. Next time when somebody wants to hit you or punch you, just run forward, sorry, in the opposite direction, sorry, run away from the punch, so that even though the punch gets you, the impact is small. If you tend to wait and then takes you down, then this is the thing. And then if you want to remain stationary, then the impact becomes higher. So those are some of the things that we are looking out for in terms of overflow. Then also we have what we call the Euler equation. Now when we are discussing the different forces, we are discussing them from, we're saying there is a force as a result of pressure, there is a force as a result of weight, and then there is an external force. These ones have been derived. But at the end of the day, we are saying that when we have this kind of scenario, it is bringing us to the binary equation, that if you have all those three forces, and we assume that if it is a counter force, if we are conserving momentum, this acting in the opposite direction to this, then we are conserving momentum. So this kind of thing here we are saying that this is conservation of momentum, and this conservation of momentum for a frictionless fluid using an Euler equation, when you derive it, it brings us to an equation of what we are calling a binary equation. So this binary equation is based on two properties: a frictionless fluid, and we're saying that the same properties are constant in a system from one point to another as long as there is flow. Thank you.